welcome to this video. Today we're going to talk about a power of a point. We're also going to talk about what's a radical axis, a radical center, and at the end also show an example of how to use those to solve an actual problem. So this is something in geometry. So we're going to start by proving a theorem. Suppose you have some circle. Alright, it's good enough. A circle omega. And suppose some point A, it could be inside the circle, could be outside the circle. It doesn't matter. But the theorem says if you draw a chord, any chord, through any chord of the circle that passes through the point A, so say this is our point A, and let's label these by B and C, then it says that A times B and A times C will be the same no matter which chord you pick. So you can think of it as maybe we rotate this line, and then we choose the intersection points with the circle and we multiply the appropriate lengths. It'll be the same. So let's prove that for a point outside the circle, and I'm going to leave it for you to do a similar thing inside the circle. So I'm going to what I'm going to do is actually show that all of these, so this AB times AC is equal to the length of the tangent squared. Because you can think of it that as like we rotate this line and it gets closer and closer to the edge of the circle. These lines A, B, and AC start to get closer and closer together, like until B and C are the same point, and we're multiplying just AB times AB, which is the exact tangent squared. So we're going to show, let's call this point D. We want to show AB times AC is equal to AD squared. So let's first of all draw CD. And now I'm going to, here, so this I'm going to label O as the center of the circle. And I'm also going to draw line BD. So let's call this angle alpha and this angle beta. And basically what we're going to do is just a bunch of angle chasing. So let's see. So we know this angle ADO, since this is a tangent and OD is a radius, we know this is 90 degrees. So the angle ODC, which is a bit tough to see there, ODC is 90 degrees minus beta minus alpha. And now I can also say, since OD is equal to OC, I can say that angle OCD is also 90 degrees minus beta minus alpha. And so I can say that angle DOC is 180 minus the sum of these, which is 2 alpha plus 2 beta. So this is this angle. And now I know that this angle is going to be 2 times an interior angle, which leans on the arc CD. So if, say this is some point, I know this angle will be 1/2 of this angle, but I also know CBD, the angle CBD will be 180 degrees minus this angle. And so angle CBD is 180 degrees minus angle DOC over 2. angle deuce is 2 alpha plus 2 beta, so this is 180 degrees minus alpha minus beta. Now if this is beta, and this is 180 degrees minus alpha minus beta, that means that angle BCD is alpha. But what was alpha originally? Alpha was this angle ADB. So we've actually shown that angle ADB is equal to angle BCD. Now we're going to use similar triangles. Let's look at triangles ABD and ADC. This angle is obviously equal to itself, and this angle is equal to also the appropriate angle, which is this one. That's what we just proved. So these are the same. And so now I can say that by the ratio of similar, that because they're similar triangles, the ratios of the appropriate side lengths are the same. So I can say that AB divided by AD, because AB goes to AB, so I'm going to write this actually. So triangle ABD similar to triangle ADC. So AB divided by AD is the same as AD divided by AC. And so we multiply by 18 by AC, we get that AB times AC is equal to AD squared. And so we've indeed shown that that's the case. We managed to prove this. But now we can say, BC was any chord, we chose some random chord BC. This applies for any chord. So if we picked another chord with intersection points D and E, with intersection points E and F, we would have AE times AF is still AD squared. And so AB times AC would be AE times AF, and indeed that size of this length times this length is always conserved, even in the case of a tangent, because that's exactly what we proved. In the case where the point is inside the circle, which again I'll leave for you to do, the chord will look like this. And if this is A, this is B, this is C, and you want to show AB times AC, no matter which chord you choose, is the same. The way to do that, as sort of a hint, is to pick another chord, D and E, so DE, and show that AB times AC is AD times AE, meaning that that length is conserved. And I also recommend using a similar thing with showing two specific triangles are similar and using the ratio of appropriate side lengths. So that's what we've shown. Now, from this, we can define some function. And the function is going to be called the power of a point. I'm going to denote it by J. So, J omega A. So this is with respect to the circle omega at the point A. This is exactly this size, AB times AC, or if you want AD squared, it's the same, of A if we look at with respect to the circle omega. And if A is outside the circle, this will be positive. If A is inside the circle, you actually do the negative. So for A here, if we look at this point A, so say, let's call this omega tilde. So J omega tilde would be negative AB times AC. That's just the definition. And if a point A is exactly on the surface, on the circumference of the circle, so if this was our point A, then its power is considered 0. So that's it for the definition of a power of a point. Then we're going to move on to what is a radical axis. Okay, now let's talk about what is a radical axis. A radical axis is a family of points that corresponds to any two circles. For any two circles, we'll define the radical axis as the family of points whose power with respect to one circle is the same as its power with respect to the other circle. And so first of all, I'm going to show that if the two circles intersect, then the radical axis will just be the line that passes through both intersection points. So first of all, I need to show two things. Any point on the line is on the radical axis, and any point that is on the radical axis, so it satisfies that the power from with respect to this circle is the same as its power with respect to this circle. I'll need to show that all of those points are also on that line. And that will show me that the radical axis is that same line. So let's begin the first one. Let's label the intersection points by A and B. Now, take a point C on the line. And so let's say it's outside of the area between the circles. Then the power of C with respect to this first circle, well, I can choose any chord I like. I'm going to choose this chord, the chord that passes through the chord AB. I can do that, yes. So the power of the point C will be AC times BC. So that's with respect to this circle. What about this circle? Well, again, I can choose any chord I like. I'll choose again the chord AB. And so the power with respect to the second circle will also be AC times BC. And these are obviously equal. So indeed the power of the point C with respect to this is the same as its power with respect to this. Now, I assume C was not in between A and B. Now let's look at a point D that is between them. So the power of D with respect to the first circle is negative AD times DB. And because I can choose this chord, so it'll be this times this with a minus sign. And its power with respect to the second circle, again, I'll choose this chord AB. It'll be negative AD times DB, which again, obviously, these are equal. So indeed, and of course, I have to check the points A and B specifically, but obviously, the power of point A with respect to both circles is 0, and the same for point B. So indeed, all points on this line are on the radical axis. Now I'm going to show that any point that is on the radical axis, so take some point, let's take some point E. So let's take this point E, and we'll show that it has to be on the line. So I'm going to draw, I can pick any chord I like. I'm going to take a chord that passes through B. So let's label this as F. I have EF times BF, and we know this is supposed to equal to, this is a straight line, not very straight, but whatever. This is G. I know EF times BE. So this times this. I know this has to equal this times the entire EG. So I have BE times GE. I know these need to be equal since it's on the radical axis. These cancel out. EF is equal to EG. And as you can see, that really that's not the case unless E is on the line. Because remember, F and G are the intersection points if you take a chord through B that passes through E. So you take the line BE, and where does it intersect in this point? At this circle. Where does it intersect in this circle? Because E, F, and G lie on this, are on the same line, and EF equals EG, and EF is equal to, supposedly EF is equal to EG. Here it's clearly not true. If we suppose E is on the radical axis, if EF is equal to EG, since EF is EF and G are on one line, and like F and G are on the same side of that line with respect to E, we know that F has to be the same point as G. But if F is on the point on this circle and G is on the point on this circle, if they're the same points, they have to be the second intersection point A. Meaning that E, B, and A are on the same line. So this, and so we prove that any point on the radical axis is on the line. Meaning that we proved that the radical axis is just this line that passes through A and B. Okay. Now, let's move on to a radical center. Okay, now we're going to talk about a radical center. So radical center is something that corresponds to three circles. So we have three circles, and each pair of them has a radical axis. So these two, and these two, and these two. That corresponds to three lines in the plane. And the claim is, what we're going to prove is that these three lines intersect in one point. So this is what we're going to do. So we're just going to draw two of them, mark the intersection point, and show that the third radical axis also intersects at that point. So let's draw this. So this is the radical axis of these two, and this is the radical axis for these two. And now we're going to show that the radical axis of these two also intersects at this intersection point. Let's label it O. So we know by the definition of the radical axis, so let me mark these circles, so omega 1, omega 2, and omega 3. So we know that the power of O with respect to omega 1 is equal to the power of O with respect to omega 2, since it's on its radical axis. And furthermore, the radical axis with respect to omega 1 is the same as the power, not the radical axis. The power with respect to omega 1 is the same as the power with respect to omega 2. And the power with respect to omega 1 is the same as the power with respect to omega 3. So, and again, because it's just on the radical axis between omega 1 and omega 3. But these are obviously equal. And this is equal to this, which is obviously this, which is equal to this. So these two are equal. So the power of the point with respect to omega 2 is the same as the power of the power of this point with respect to omega 3. That is by definition, that means that by definition, O is on the radical axis of these two circles. So indeed, if I draw this, we get that these three intersect in one point. Which is interesting because if, like in this diagram, if any two of them intersect at two distinct points, we have that that the line between these intersection points, and these intersection points intersects at one point, and didn't even have to mention the word radical axis. But if you do use the fact that these are these radical axes, you write two equations and you're done. And this point O, which is the intersection of the three radical axes of these three circles, is called the radical center of these three circles. And now, there is also another theorem that is sort of the reverse theorem for what we just proved, and it's about how to show 4 points lie on a circle. So let's label here. Let's say this is A, this is B, let's see, this is C, this is D, this is E, and this is F. So we basically know A, B, C, D, and E, F intersect in 1 point. But now, let's assume we didn't know omega 3 was a circle. Suppose we just knew that AFBE are on a circle, ADBC are on a circle, and the three lines ABDC and EF intersect in 1 point. The theorem that we're going to prove says that the points EDFC are on a circle. And it's like the reverse theorem for what we proved. So let's begin. What we're going to do is discard one of the points, say the point C, and think about how can we get the point C. So maybe we fix the other points in place. So we fix the points A, B, D, E, and F in place. And we ask, well, how from them can we actually get the point C? Well, we know 2 things about C. It's on the circle it's on the circumcircle of ADB, and it's on the line DO, where O is the intersection of AB and EF. And we know that, and so it's the intersection of a line, that's DO, and a circle, meaning that it has 2 options. So, but the first option is our point D, and C has to be distinct from D, and so we know that C has to be the other intersection point, and so C is actually uniquely defined. If say there are here are the points A, B, D, E, F, and then we know A, B, C, D are on a circle, and A, B, E, F, and C, D intersect in 1 point, and C is not D, we can uniquely get the point C. But now, so that means if the point C is determined by these 5 points, if we find another point that is also on the line DO and on the circle ABD, then it has to be the point C. Now, but what I'm going to do is to take the point, instead of C, I'm going to take another point, say H, which is on the circle EDF, on the circumcircle of EDF, and on the circumcircle of ABD. So it already satisfies one condition, it's on this circumcircle. But another thing that we know is, because what we just proved of the radical axes, AB, EF, and DH intersect at 1 point O, meaning that DOH are on the same line. In other words, H is on the line DO. But so now we found another point H, which is on the line DO and on the circle ADB. So H has to be the point C. But remember how we defined H? We defined H to be the point which is also on the circumcircle of EDF, meaning that H, D, E, and F are on one circle. But if H is our point C, because again we uniquely defined it by the intersection of this line and this circle, and we showed that H also is the intersection of this line and the circle, so H is C, but that means that C, D, E, and F are indeed on one circle. So just to reiterate the theorem that we now proved, suppose you have 6 points in the plane, A, B, C, D, E, F. A, B, C, D, and E, F intersect in one point. A, B, C, D lie in a circle, and A, B, E, F also lie in a circle. There. The theorem says that C, D, E, and F also lie in a circle. So that was what we just proved. But now you might be wondering, alright, we defined all these radical things, these axes, that center, the power of a point. How does this help to actually solve a problem? Solve geometry problems. Well, that's what we're going to do. The final thing we're going to do now, after all of this, is just do an example and see how from a geometry problem that seems maybe annoying, or like it would be a lot of angle tracing or calculating things with geometry, can be easily solved with some of these, this one radical center and a couple of radical axes. So let's erase the board, draw the problem, and solve it. Okay, so now we're going to do this problem. So it goes as follows. You have a circle and two rhombuses sort of inscribed in it. So you have like these 4 points. So like these two opposite points are on it. These pairs don't necessarily have to be on it, on the big circle. These are two rhombuses and they have like the same side length. So this side length is equal to this side length, and since these are rhombuses, these are also this is equal to this, which is this and this, and it's also equal to this and this and this and this. These are all the same length, and but keep in mind these rhombuses don't have to be the same. These angles could be different. This could say be 30 degrees, this could be 20 degrees, and the question would still work. That's all we're given, and we need to show that these 4 points lie in a circle. Like there's just the green circle in the diagram. So this seems a little hard, but we can use what we just proved. So we're going to find another pair of points which form a circle which together with these form a circle, and if we make them into a line, this, and that pair of points intersect at that one line. So it takes a little bit of tinkering to do that, but what I'm going to take first of all 2 circles. Now we have the circle with, or at least an arc of the circle with this center and with these 2 points being on it. So this is like part of the circle, and we also drew another part of the circle. We did a similar thing for the red rhombus. So it's this. So it had this as the center and intersects these 2 points. So now what I'm going to show is that the center of the big circle, the black one, so label it like here. I'll show that this point is on the radical axis of these 2 circles, the blue one and the red one. So this is actually pretty easy to show, since these 2 rhombuses have the same radii. So if this is, say, radius r, and this is radius, so this is radius r, this is also radius r, meaning that, and so the actual thing we've drawn here is, say, this is the big circle, and say this is like the blue one and this is the red one. They have like the same radii, meaning that this is like just a rotation of this one. So this point is like symmetric to both of them. So if you can like draw tangents or whatever you want, it doesn't matter. These they're gonna be the same. Here it looks like these tangents are the radii. They don't have to be the radii of the big circle, but because this is like a rotation to this one, and this is the center of the circle, it's like symmetric to both of them, so it has the same power to both of them, so it's on the radical axis. So this point, the center of the circle, is on the radical axis of the red circle and the blue circle. And now I can also say that these 2 points, like these 2 pairs of points, these red ones and these blue ones, also intersect at the center. Why? Well, this is a rhombus, so this line is the perpendicular bisector of these 2 points. But these 2 points are in a circle, meaning that their perpendicular bisector passes through the center of the circle. Meaning that these 2 points, the line passes between them, also passes through the center, and the same goes for the red points. So the center of the circle is on the radical axis of these two, of the red and blue circle, and it's also on this line and on this line. But now notice, so what we have here is these 2 points are on this circle, these 2 points are on this circle. So this point is like the intersection of, so this point is like the intersection of this line, and like the radical axis of these 2 circles, which is like gonna be a line like this. So by what we proved previously, so these are like our points. These are like our points C, D, E, and F, and these are like our points A and B. So we know. So now, like A, B, C, D, E, F intersect in one point. We know A, B, C, D are on a circle. A, B, E, F are on a circle. So by what we proved, C, D, E, and F are on a circle. And so these 4 points, by what we proved, are indeed on a circle. And as like a bonus, I guess, this point, the center of the circle, is the radical center of the circle that passes between these 4, like this and this blue circle and the red circle. But yeah, that's the solution to the problem. And finally, that's it. If you want more content like this, please subscribe to my channel. I'm uploading more interesting problems and things like this in the future. And finally, that's it.